Extension cords and anesthetizing locations are generally not permitted according to the current edition of NFPA 99, which is the 2021 edition. This is a critical update from earlier editions, so it's important to be aware of the most recent standards. Regarding the maximum length of portable electrical appliance cords, the 2002 edition of NFPA 99, as you mentioned, didn't specify a length limit. However, current standards differ. The NFPA 99 2021 edition refers to NFPA 70, which is the National Electrical Code. NFPA 70 imposes restrictions on cord lengths. The National Electrical Code typically limits the length of portable electrical appliance cords to 6 feet. Therefore, following the updated code, the length of portable electrical appliance cords used with medical devices and anesthetizing locations should not exceed 6 feet. Now let's discuss line isolation panels, or LIPs. They are required in anesthetizing locations under specific electrical conditions. Specifically, line isolation panels are necessary when the electrical potential to ground exceeds 300 microamps. This requirement is related to electrical safety in critical care areas and is not exclusively determined by whether an operating room is classified as wet or dry. The primary function of line isolation panels is to limit the amount of current that can flow to ground in the event of a fault, thereby minimizing the risk of electrical shock to patients and staff. The decision to install line isolation panels hinges on the potential electrical leakage, not just the presence of moisture. Electrical leakage refers to the unintended flow of current from an electrical device to ground. In a properly functioning electrical system, current flows through the intended circuit, but insulation failures or other faults can cause current to leak to ground through unintended paths. This leakage current can pose a safety hazard, particularly in healthcare settings where patients may be more susceptible to electrical shock due to the use of invasive medical devices. These devices often involve direct connections to the patient's body, increasing the risk of harm if leakage current is present. Leakage current is measured in microamps, which are 1/1,000,000th of an amp. Healthcare facilities often have strict limits on the amount of leakage current allowed in patient care areas to ensure safety. Line isolation panels are designed to reduce the amount of leakage current that can flow to ground in the event of a fault. They work by isolating the electrical supply to the patient's care area from the building's main electrical system. This isolation reduces the potential for ground faults and limits the amount of current that can flow through a person who comes into contact with a live conductor in ground. The line isolation panel contains a transformer that isolates the power supply to the operating room. This transformer has a high impedance which limits the amount of current that can flow in the event of a ground fault. The panel also includes a line isolation monitor, or LIM, which continuously monitors the impedance of the isolated power system. If the impedance drops below a certain threshold, indicating a potential ground fault, the LIM will activate an alarm. This alarm alerts staff to the presence of a fault and allows them to take corrective action before a patient or staff member is harmed. The alarm will usually go off well before the 300 microamp threshold is exceeded. Wet locations are defined in the National Electrical Code, NEC, as areas where water or other liquids are present. The NEC provides specific requirements for electrical equipment and wiring in wet locations to prevent electrical shock and other hazards. Examples of wet locations in healthcare facilities include hydrotherapy rooms, areas where patients are frequently bathed, and certain areas in operating rooms where fluids may be present. However, the presence of a wet location does not automatically trigger the requirement for line isolation panels. The determination of whether line isolation panels are needed depends on the potential for electrical leakage and the specific requirements of NFPA 99. Dry locations, conversely, are areas where water or other liquids are not normally present. Dry locations typically do not require the same level of protection as wet locations. However, it's important to note that even in dry locations, electrical safety is still a concern. Equipment must be properly grounded, and electrical circuits must be protected by ground fault circuit interrupters, or GFCIs, in certain areas to prevent electrical shock. GFCIs are devices that monitor the current flowing through a circuit and quickly interrupt the power if a ground fault is detected. They are commonly used in bathrooms, kitchens, and other areas where water may be present. It is important to understand the distinction between wet and dry locations and to comply with all applicable electrical codes and standards to ensure the safety of patients and staff. Anesthetizing locations are defined as areas where flammable anesthetics are used. These locations pose a unique fire hazard because flammable anesthetics can easily ignite if exposed to a spark or other source of ignition. To prevent fires in anesthetizing locations, special precautions must be taken, including the use of explosion-proof electrical equipment and the elimination of static electricity. Explosion-proof equipment is designed to contain any sparks or explosions that may occur within the equipment, preventing them from igniting the surrounding atmosphere. Static electricity can be generated by friction, such as when people walk across a carpeted floor. To prevent static electricity buildup, conductive flooring and grounding straps are often used in anesthetizing locations. These measures help to dissipate static electricity and prevent it from accumulating to dangerous levels. NFPA 99 provides specific requirements for anesthetizing locations to address these hazards. These requirements include the use of isolated power systems, line isolation monitors, and other safety measures. Isolated power systems are similar to line isolation panels in that they isolate the electrical supply to the anesthetizing location from the building's main electrical system. This isolation reduces the potential for ground faults and limits the amount of current that can flow in the event of a fault. The line isolation monitor continuously monitors the impedance of the isolated power system and alerts staff to the presence of a potential ground fault. The requirements for line isolation panels in anesthetizing locations are typically more stringent than those for their patient care areas. This is because anesthetizing locations pose a greater risk of electrical shock and fire. It is essential to comply with all applicable codes and standards to ensure the safety of patients and staff in these critical care areas. Microamperes are units of electrical current equal to 1/millionth of an ampere. The electrical current is the flow of electric charge through a conductor. It is measured in amperes, which are defined as the amount of charge that flows past a given point in 1 second. 1 ampere is equal to 1 coulomb of charge per second. Microamperes are used to measure very small amounts of electrical current, such as leakage current in electrical equipment. Leakage current is the unintended flow of current from an electrical device to ground. It is often caused by insulation failures or other faults in the equipment. Leakage current can pose a safety hazard, particularly in healthcare settings where patients may be more susceptible to electrical shock. The human body is sensitive to even very small amounts of electrical current. A current of just a few milliamperes can cause pain, muscle contractions, and even cardiac arrest. For this reason, healthcare facilities often have strict limits on the amount of leakage current allowed in patient care areas. These limits are typically expressed in microamperes. Line isolation panels are designed to limit the amount of leakage current that can flow to ground in the event of a fault. They work by isolating the electrical supply to the patient care area from the building's main electrical system. This isolation reduces the potential for ground faults and limits the amount of current that can flow through a person who comes into contact with a live conductor and ground. The line isolation panel contains a transformer that isolates the power supply to the operating room. This transformer has a high impedance which limits the amount of current that can flow in the event of a ground fault. The panel also includes a line isolation monitor which continuously monitors the impedance of the isolated power system. If the impedance drops below a certain threshold, indicating a potential ground fault, the line isolation monitor will activate an alarm. This alarm alerts staff to the presence of a fault and allows them to take corrective action before a patient or staff member is harmed. The alarm will usually go off well before the 300 microamp threshold is exceeded. The maximum allowable leakage current in patient care areas is typically specified in NFPA 99. The NEC also provides requirements for electrical safety in healthcare facilities, including limits on leakage current. The NEC and NFPA 99 should be consulted to ensure compliance with all applicable codes and standards. Healthcare facilities must implement a comprehensive electrical safety program to protect patients and staff from electrical hazards. This program should include regular inspections of electrical equipment, testing of leakage current, and training for staff on electrical safety procedures. By following these procedures, healthcare facilities can minimize the risk of electrical shock and ensure the safety of patients and staff. The National Electrical Code, or NEC, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC provides detailed requirements for all aspects of electrical installations, from the size and type of wiring to the grounding and bonding of electrical equipment. The NEC is not a law itself, but it is often adopted by state and local governments as part of their building codes. This means that compliance with the NEC is legally required in many jurisdictions. The NEC is divided into chapters, articles, and sections. Chapter 1 covers general requirements such as definitions, scope, and organization. Chapters 2 through 7 cover specific types of electrical installations such as wiring methods, equipment, and special occupancies. Chapter 8 covers communications systems such as telephone and data wiring. Chapter 9 contains tables and examples for calculating electrical loads and conductor sizes. The NEC is a complex and comprehensive document, and it is important to consult it carefully when designing and installing electrical systems. The NEC is intended to protect people and property from electrical hazards such as fire, shock, and electrocution. It provides requirements for the safe installation of electrical wiring and equipment to minimize these risks. The NEC covers a wide range of electrical installations, including residential, commercial, and industrial buildings. It also covers special occupancies such as healthcare facilities, hazardous locations, and swimming pools. The NEC is constantly evolving to keep pace with new technologies and changing electrical safety practices. The NFPA Technical Committee on the NEC meets regularly to consider proposals for revisions to the code. These proposals are submitted by a variety of stakeholders, including electrical contractors, engineers, manufacturers, and code officials. The NEC is a valuable resource for anyone involved in the design, installation, or inspection of electrical systems. It provides clear and concise requirements for the safe installation of electrical wiring and equipment. The NEC is an essential tool for protecting people and property from electrical hazards. NFPA 70 is the formal designation for the National Electrical Code. It is the document itself. This is to avoid confusion. The terms NFPA 70 and NEC are often used interchangeably, but it is important to remember that NFPA 70 is the official name of the code. The NFPA develops and publishes hundreds of codes and standards, covering a wide range of fire and electrical safety topics. The NEC is just one of these codes and standards. NFPA 70 is the most widely adopted electrical code in the United States and is used as a model code by many other countries around the world. The NEC is constantly being updated to reflect the latest advances in electrical technology and safety practices. It is important to stay up to date on the latest edition of the NEC to ensure compliance with current electrical safety standards. The NEC is an essential tool for anyone involved in the electrical industry. It provides comprehensive guidance on the safe installation and maintenance of electrical systems. By following the requirements of the NEC, electrical professionals can help to protect people and property from electrical hazards. In summary, it's best to stay updated with the latest editions of NFPA 99 and NFPA 70, as well as local regulations, to ensure compliance and maintain the highest level of safety in healthcare facilities. The 6-foot limitation on medical equipment codes will help improve the safety of the area in question.